What's up, everybody? Welcome to lecture 25 over section 5.2. It is lecture 25, right? I'll have to check that later. Anyhow, welcome to whatever numbered lecture this is. It's over section 5.2 in this idea of volume. And we're talking, of course, about the volume of some sort of a solid shape, right? Not the volume of your hair or the volume of your music. But this idea of volume properly in the sense of like what the volume of some solid thing is. So when talking about volume, it's going to help to have some pictures for us, to have a general idea of what we're going to be doing all throughout this section and next section, I should say. Let's start off with, let's imagine we wanted to know the volume of a sphere. Those of us who like to memorize formulas probably have that formula memorized. But where does it come from? Well, one thing we could do is we could start by approximating the volume of that sphere. We could do that by saying, let's set up a coordinate system so that the x-axis is moving this way, right? The y-axis is coming out of the board and the z-axis is up. This is just to give us some sense of orientation here. Now, as we move along the x-axis, let's take and break up our solid with a bunch of disks. We're going to approximate slivers of our volume with disks. Those disks are going to have a volume, the disks are going to have a volume equal to the cross-sectional area of each disk multiplied by the width of that disk. So that's what you've got here in this picture, right? This is a cross-section of this sphere. This sphere has, or this disk inside the sphere has a width of delta x and a cross-sectional area of a at xi. So whatever that cross-sectional area is, we can talk about that later. So if we took and used these disks to form all these little tiny cylinders to approximate the volume of this sphere, that would look something like this, right? You're just going to take the cross-sectional area of each of those cylinders, multiply it by the width of each of those cylinders, and then you're going to add them up. Well, this looks familiar, doesn't it? This looks like it's leading up to something like the integral, and that's because it is. The volume of any solid, properly said, is equal to the integral from a to b, the cross-sectional area, integrated with respect to x. This thing is equal to the limit as n approaches infinity of the sum of a x sub I, a at x sub I, times delta x, where delta x is defined in our usual way. So this is what volume is equal to properly. Now this is what, like I said, this entire lecture video will be about, and what the next lecture video will be about. It's just this idea. We're going to talk about a very particular set of solids. We're going to be talking about solids that are formed by acts of revolution. So you're going to take a graph and revolve it in a particular way to form these solids. So these are going to be symmetric shapes that kind of look cylinder-y maybe, or spherical. They're going to be symmetric though. Symmetric about some axis. So you're just taking a strip of a thing and rotating it about some line to form this structure. Some examples would be like a cone, a sphere, a cylinder, PVC pipe is an example of this, right? Because you're taking a sliver, just like that one strip, and revolving it about some line to create the pipe itself. Now, the way we're going to talk about these, it might feel like there's three distinct different ideas here. There's actually two. The first two that we're going to talk about today are really the volume equivalent of how we were talking about area in the videos last week. In particular, the area between two functions. The next video will go over another method for evaluating the volume of an object. But with that said, let's check out some of this stuff. So in the notes to help explain some of this idea, I start with an example of a sphere and build up the problem from there. But I don't think that's the easiest example to see. And the reason why is because you have to do some rearranging of some terms. And then you get to the point where you can be like, oh, this is my area function and blah, 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 blah. It's a mess. That said, don't sleep on that example, guys. That example is a great example. I just think this one will be a little bit better for a lecture video. So in this example, we're taking some function equal to some slope, m, times x. So it's just a line that goes through the x-axis. Okay. We've got this example here. And what we're going to do is we're going to rotate all of the area underneath our function so all of this in blue, we're revolving about the x-axis. And I keep saying rotate, I mean to say revolve. Rotate and revolve are very different terms. But we're going to take a revolution of this about the x-axis. And when we do, we're going to get a cone that looks something like this. And we need to find the volume of that cone. We know the volume of this thing from what we just saw in the last video is going to be equal to, since A starts at 0 here and we end at B, it's going to be equal to the integral from 0 to B of whatever a cross-sectional area of a disk would be, integrated with respect to x. Okay. How does that help? Well, it helps by just giving us the structure we need to start with, right? Like we know what the integral needs to look like. And we need to figure out what this area of x is. And we know this area of x is going to be the area of any given disk, cross-sectional disk, within our solid, right? So as we move along the x-axis, what's the area of one of those cross-sectional disks? Well, these are disks. So their area is going to be equal to pi r squared, right? Oh, that doesn't tell us how this relates to x. We do, however, know that radius is going to need to be a function of x. That's about all it tells us. So we look at this picture for a little while and think about it. We say, you know what? Let's ignore that z-axis. Let's just focus in on the xy axis and project it back into two-dimensional space. So let's go back to this picture. Let's compare these. The radius of one of these disks would correspond to this line, right? Well, that line, this line in green, that's probably hard to see, and I apologize for that. This line has a height of f of x. So radius here is equal to your function evaluated at x. In other words, the area, the cross-sectional area of any of these disks is pi times your function squared, which now gives us the rest of this formula, right? Now we have the integral from 0 to b of pi times f of x, that quantity squared, integrated with respect to x. And I'm just using a dummy variable, but in a problem we would of course define what a and b both are. And this is how we find the area of revolution, the volume of revolution. This is one method, I should say. So from here, we can figure out the rest of this problem. We say, cool, this is equal to the integral from 0 to b of pi times, well, our function was some slope times x, that quantity squared. Once we distribute the square onto the m and onto the x, we'll see that pi times m squared is a constant, so we can pull those out. To get the following integral, right? Well, this thing's pretty straightforward to integrate, isn't it? This is going to end up giving us, choose a piece of chalk. This is going to give us pi times m squared times the quantity 1 over 3 times x cubed evaluated from 0 to b. And that's it. We just have to do the algebra now. Everything disappears at 0, so we would be left with pi times m squared times 1/3 b cubed. That's it. That's what the volume of this particular cone would come out to be. And this cone is formed by revolving the area underneath the function m times x from a equal to 0 up to b about the x-axis. That's what the volume of that shape would be. That's it. That's all there is to this. Okay, that's all well and good, but what happens when we want to start talking about things like shells? So for example, that PVC pipe example I gave you. How do we find the volume of those things? So an example of this would be, you're going to have to forgive the drawing. It's not going to be the best. I will have to admit that in advance. Way not good. So it would be like a cylinder with a hole cut through it, right? Yeah, that's a bad drawing, I know. I tried, but how will we find the volume of that thing? Well, stay tuned and let's find out. Stay tuned and we will find out. I'll set the example up. I'll be right back. Now, in this other example, what we're doing is we're taking an area between two functions and revolving it about the x-axis to form a new solid, namely this ugly thing. It's ugly as shit. Anyhow, so we got this thing. We want to know the volume of it. Well, it's hollow. It's irregular, but it's symmetric about the x-axis, right? It has that revolution there. How are we going to find that volume? Well, to figure that out, we might want to instead consider this other example over here. So here we've got a cylinder with the center of it pulled out, right? So it's just that shell. So again, a pipe example. And intuitively, we know that the volume of that pipe is the total volume minus that missing volume, right? So the total possible volume from the outside minus the missing volume. And writing this in that integral notation that we were just talking about, that would look something like this. Except, there's one thing that needs to be changed here. We need the absolute value. I had a typo, that's all. The reason why it works out this way is because the way we have all of this set up in this particular example, because it's regular, it's a regular shape, right? There aren't weaving in and out between the functions. You don't actually need the absolute values in this example, but for what we're going to be doing and for what the actual proper definition is, we do. So because of this, we have this absolute value, right? So it's the integral from A to B of the absolute value of the difference of the two areas integrated with respect to whatever axis you're rotating about. In our case, of the cylinders here, of this cylinder rather, we're rotating about the y-axis. So everything's in terms of y. So just to give a little bit of insight though. So what it looks like we're saying then is we need the whole area, the area of that largest piece, minus the area of that interior piece. And yeah, that's exactly what this formula is getting at. Now applying that to here, we might step back and look at it for a little bit, but what this is going to come down to is this is the integral, or this volume rather, is going to be equal to the integral from A to B of the absolute value of the difference of areas. So let me write all this out. Trying to write and talk at the same time, not my strong suit. So let me write this out first. What we've got is area 1. It would be easier if I did this. Area big of x minus area small of x absolute value dx, right? But the areas here are going to come out to be, let me actually write it over here now, the integral from a to b of the absolute values. The biggest area is pi times f squared of x minus the smallest area is pi times g squared of x. And this is all integrated with respect to x. Now why is it that the big area is pi times f squared of x and the smallest area is pi times g squared of x? Well, the reason why is because look at what we've got. If we were to take a single cylinder, rather a single disk, for the cross section of the largest piece, that whole piece that goes all the way to the outside, this thing has a cross-sectional area of pi times f squared of x. And that's for the reasons that we just saw in that previous example, right? The example before I got to all this stuff. Now, the area for the interior piece, I'll use a piece of white chalk. That'll work. This cross-sectional area is equal to pi times g squared of x. Again, same thing as that last example. So we know the cross-sectional area of the big piece, we know the cross-sectional area of the small piece. So plugging all of this together now, we get this following integral. And that's all there is to it. Now, having said that, what you're looking at here with this integral is what's called the washer method. Generally called the washer method. I dropped what I was going to say. Give me a second here. It's late. It's like midnight, 12:30, so I'm a little forgetful at the moment. So the washer method is this thing here, right? And that previous example was just a special case. That's what I wanted to say. That previous example was a special case of the washer method. But beyond that, I really don't have much to say. Just wanted to clarify some of what might have been in the notes. It might have been confusing to y'all. Might have been in the notes. Some of what was in the notes, but might have been confusing to y'all. But beyond that, yeah, if y'all have any questions, by all means, as always, drop me an email, stop by office hours. I did want to remind y'all, you have 2 weeks left of the semester. 2. The final is on the very last Friday of the semester. Don't forget that. Your homework is all due then. When I last looked at the grades, only about half of y'all were caught up on the homework. So get on top of it. But beyond that, that's all I got for y'all. I guess have a good rest of your day, everybody. Later.